Hello, everyone. So today we want to start a new topic called the Laplace transforms. So the goal, again, is to solve an ODE. So Laplace transforms is a method to solve ODEs. So recall that a linear ODE can be written as, let's say, y-nth derivative plus Pn minus 1 of x, yn minus 1 derivative, all the way to, let's say, P1 of x y prime plus P0 of x times y equal, let's say, some f of x. So let's consider a linear ODE of this form, and we want to see how we can use a Laplace transforms in order to solve this equation and find y. So the goal is to find y. The solution of ODE above. So here, Laplace transform, basically, if I want to describe it, is a type of function whose inputs and outputs are functions themselves. So usually when you saw about the concept of functions before, usually the inputs and outputs are numbers. So when you had, for example, f of x equals 2x, the input was a number, the output was also a number. But here, inputs and outputs are functions. So here in this chapter, we will have transforms. So normally, instead of function, we can call this type of function transforms or functional. Functional means is a function whose inputs are functions themselves, or functions whose inputs and outputs are functions. Functions with function input. You have seen examples of such functions or functionals, or sometimes also called the operators, before. So here we have, remember that in pre-calculus we saw that each function acts like a machine. So here also our function, let's say here in this case Laplace transform, is acting like a machine, but this time the input and outputs are both functions. So the input, basically, we can feed it the function that we want to find it, let's say y of t. If we work with, let's say, a domain of t, previous chapter we also worked with t, but we can also replace the here with t. So we feed, let's say, y of t to our Laplace transform, and then the output is also a function, which we can call it, let's say, capital F of s. So inputs and outputs are functions. Now we could ask, what's the point of this transformation? If the inputs and outputs are both functions, then what's the point of applying such a transform? Well, the answer is, when we start with original function y of t, and there are some derivatives here in the ODE that in general makes the ODE complicated to solve. dealing with these derivatives. Like, you know, we have first order derivative all the way to nth order derivative. But the good news is once we apply this transform, we get these new functions, capital F of S. And in this new world of functions, you know, that we go basically from a universe of T's to universe of S's. Then in this new world, there is no derivative appeared. All the derivatives will be disappeared once we apply the Laplace transform. And we get an equation, we get an algebraic equation where there is no derivative appeared there, and we can easily solve for capital F of S. Once we solve for capital F of S, we can go back to our original function y of t by applying another transform called inverse Laplace transform. So inverse function, you know that it has the property that it changes the input to output and output to input. So we can go from output F of S to the original input y of t once we apply inverse of this transform. Of course, we have to show that this transform is invertible, which would happen, as you know, if it's 1-to-1. We will show that, and once we show that, we can conclude that it has an inverse, and then apply the inverse to get the original function back. So if I want to, I'll explain about the details later, but for now, let me just mention the idea very briefly, that the Laplace transform disappears all the derivatives and we can solve for F of S, capital F of S, via an algebraic equation and after that we can apply another transform called inverse Laplace transform to derive the original function y of t. So we apply Laplace transform, we get the function F of S, and then we apply inverse Laplace transform, we get the original function back. So here is what we said here. So again, I want to emphasize that when you want to solve for F of S, there will be no derivatives appeared. For example, let's say if you have S squared F of S plus F of S equals, for example, 2. Let's say rather, instead of, for example, y double prime plus y equals, let's say, 5, which is an ODE, because the derivatives are appeared. Let's say if you want to solve for this equation instead. So here, see, in this equation, there is no derivative. So it's just an algebraic equation. You want to solve for, let's say, F of S, you can just simply factorize F of S, and then F of S times S squared plus 1 equals 2. And then F of S can be solved as 2, let's say, over S squared plus 1. But in this equation, we have to apply the methods that we learned, in the simple cases, we saw how to solve an ODE, but there are many cases that we haven't covered. And even in the simple cases, the calculation could become somehow messy and long. But here, when there is no derivative appeared, it's just an algebraic equation, we can easily solve for the function. And then we can apply the inverse transform. Once we find f of s, let's say equal to 2 over s squared plus 1, for example, then we apply inverse transform to this function to get the original function that we were looking for it. So this is the meaning of a transform with inputs and outputs that are functions. Previously, you also saw about other examples of such transform where it had inputs and outputs which were functions. If you remember, for example, in linear algebra, so in math 152, in math 252, you saw other examples of transformations that had function inputs and outputs. Function inputs and outputs. For example, the simplest example that you saw before was the derivative operator. Operator denoted by, let's say, curly D. So say for functions, we could use small letters, the normal functions, standard functions. We could use small letter, let's say small f or capital F. But normally when we have transformations where the inputs and outputs were functions themselves, in order to distinguish with the standard functions that we saw before, we usually use curly letters. So instead of small d or capital, this is small d, this is capital D. But for transformations with input and output, with function inputs and outputs, we use curly letters. So instead of small d or capital D, we use like curly D like this. Or for Laplace transform that we will define later and we will deal with it in this chapter, we use curly L. So we don't use small l, this is small l, this is capital L, but we use curly L for transformations with function inputs and outputs. So this curly D that you have seen it before, called derivative operator. How is it defined? So we know that, let's say, if D of is defined as, let's say if you want to apply D to some function f of x, this is df to dx. So for example, the derivative operator applied on x squared is d to dx of x squared, which is 2x. So as you can see, we have a transformation here. The input is a function like x squared. The output is also a function like 2x. And what is the relation between input and output? The output is simply the derivative of the input respect to x. So you also saw that this operator or this transformation is linear. The derivative operator is linear. And what was the meaning of linear transformation? So recall, t t, let's say from v to w, is called a linear transformation. If, first of all, t of v1 plus v2 is equal to t of v1 plus t of v2. And the second condition, t of, let's say, cv is equal to c times t of v. This is supposed to be true for every v1 and v2 in v. And this is supposed to be true for every c in R and v in v. So derivative operator is linear because d of addition of two functions is addition of derivatives. Derivative of addition of two functions is addition of derivatives. And derivative of a constant times a function is same as that constant times derivative of that function. So in example above, d of, let's say, f1 plus f2 is equal to f1 plus f2 derivative, which is same as f1 derivative plus f2 derivative, and can be written as d of f1 plus d of f2, and d of c times f is equal to c times f derivative. This can be written as c times f derivative, which is same as c times derivative of f. So d, the derivative operator, is linear because it has both properties appeared in the definition of a linear transformation. Now later we will see that this Laplace transform that we were talking about is also a linear transformation. So later we'll see that Laplace transform is also a linear transformation. So we will prove this later. But for now, let's define this Laplace transform. Let's say how it's defined. Once we have a function, how can we apply Laplace transform to get a new function? How is that new function defined in terms of the original function? So let's see the definition. So now let's look at the details. And we start with the definition of Laplace transforms. So definition, let f of t be a piecewise continuous function So what do we mean by piecewise continuous? if it's continuous, then it will be piecewise continuous. But even let's say if it has finitely many discontinuities, still we can consider it as piecewise continuous. In other words, if there are few intervals, let's say n intervals, let's say I1 to In, where the function is continuous on each of them. So the meaning of piecewise continuous is there are finite subintervals let's say I1 to In, such that the domain of F is union of these intervals, and F is continuous on I1 and I2 all the way to In. So F is continuous on each interval separately, and the union of and the domain of F is union of those intervals. So it's okay if F is discontinuous at the end points of those intervals or subintervals, or in other words, in the borders, it could be discontinuous, but inside each interval, F is continuous. Like I said, you could imagine like a function with finitely many discontinuities, which can be considered a piecewise continuous function. Now, for such a function, in most cases, our function in this course will be continuous, or we could have one or two discontinuities in some cases as well. So most of them continuous, or just one or two discontinuity. So these are the these will cover most of the examples that we consider in this course. Now, let's assume we have such a function. We want to define Laplace transform of this function. So then we define the Laplace transform of f of t, denoted by Laplace transform f of t, or also denoted by capital F of s, as follows. So Laplace transform f of t, which we also denoted with capital F of s, Laplace transform f of t is defined as integral 0 to infinity e to power minus st f of t dt. If this function, if this integral is convergent, see, we have an improper integral in the right-hand side. Integral 0 to infinity is an improper integral you saw in Math 114. Now, this integral, this improper integral could be convergent or divergent. If it's convergent, then we define as Laplace transform f of t. If it's divergent for some values of s, then for those values of s, Laplace transform is undefined. So this Laplace transform, as you can see here, is a function of s. Laplace transform is a function of s, and it's defined as long as this function, this integral, is convergent. So let me mention that if this integral is convergent. And if this integral is divergent for certain values of s, then the Laplace transform is undefined for those values of s. For those values of s. So let's look at an example. So I always say that whenever you want to understand a new concept, the best way is to first consider the simplest possible examples. So if you want to understand Laplace transform of a function, it's nice if you start with the simplest functions that you can imagine. Well, the simplest function we can imagine are like the constant functions. So we can, for example, consider constant function 1 and then try to find the Laplace transform of that function. So for example, let f of t equals 1 which is a continuous function. Remember, as I said, most functions that we consider in this course are either continuous or only one or two or few discontinuities. So we don't have the concern of continuity in that sense. So right now, we have a constant function, which is, of course, continuous everywhere. Then we want to define the Laplace transform of this function. So let's find Laplace transform of f of t and find its domain. Remember that Laplace transform f of t is a function itself. The answer is a function with variable s. So we want to know the domain of that function. What will be the allowed values for s? Like s can take which values? So Laplace transform f of t, as we said, is defined as integral 0 to infinity e to power minus st f of t dt. And f of t is 1 here. So this is integral 0 to infinity e to power minus st dt. And I can write this one as, let's say, limit h goes to infinity, integral 0 to h, e to power minus st dt. And antiderivative of e to power minus st, we are integrating respect to t, like, so s is like a constant here, like e to power minus 2t, for example. E to power minus 2t, what will be the antiderivative? Antiderivative will be e to power minus 2t divided by minus 2. Similarly, e to power minus st antiderivative will be e to power minus st divided by minus s. So then this is equal to limit h goes to infinity e to power minus st divided by minus s from 0 to h. And if we calculate this, so then this is equal to limit h goes to infinity. Now I have to calculate this function at this point minus this function at this point. So I have to replace t with h first, minus, then replace t with 0. And then what do we get? We get limit h goes to infinity, e to power minus sh divided by minus s, minus, now if I replace t with 0, I'll get 1 over minus s, so minus 1 over minus s. And then this is 1 over s plus limit h goes to infinity, e to power minus sh divided by minus s. Now, how much will be this limit here? Now, this limit depends on the value of s. Well, if s is 0, but if s is 0, you can see from the original expression, if s is 0, you will have integral 0 to infinity of 1, which is divergent. So we can deal with the case of s equals 0 that way. And if s is negative, minus s becomes positive. And then I will have e to power infinity here, which is also going to infinity. So in that case, I will have a divergent integral as well. Right? So the answer depends on the value of s. So the integral will be divergent if s equals 0, divergent if s is negative, because e to power infinity will be infinity. If s is 0, I repeat one more time, if s is 0, you don't need to do any of these. Just look at the original integral. If s is 0, e to power 0 will be 1. Integral 0 to infinity of 1 dt will be infinity. So in that case, we will have divergence. And if s is less than 0, I will have e to power minus, now if s is less than 0 will be negative, minus s will be positive, and h goes to infinity. So e to power positive number times infinity will be e to power infinity. E to power infinity will be infinity. So this is the reason for s less than 0. The reason for s for s equals 0 is integral 0 to infinity dt will be divergent. And finally, if s is bigger than 0, what can we say? If s is bigger than 0, then I'll have e to power minus infinity here. Because h goes to infinity, if s is bigger than 0, this will be going to infinity, times minus will be e to power minus infinity. E to power minus infinity is 0. In the limit, it will be 0. So this term will vanish, and I'll be left with 1 over s. So 1 over s plus 0, which will be equal to 1 over s. If s is bigger than 0, and the reason is limit e to power, or let me say, because I want to write something similar to the one above. The one above, I wrote e to power infinity equals infinity. Here I can say e to power minus infinity will be 0. So what I mean by this expression is that the limit of e to power minus x as x goes to infinity will be 0. I can abbreviate it as e to power minus infinity equals 0. So what does that mean? So we can say that Laplace transform f of t, which we defined it as capital F of s, is equal to 1 over s if s is positive and is undefined if s is less than or equal to 0. So then what is the domain of this function then? The domain of capital F of S is this interval 0 to infinity, because it's defined for positive numbers. So the domain is 0 to infinity. All right, now as the next example, let's look at the function e to power at for some constant a. Find Laplace transform f of t, which we can denote it with capital F of S, as we saw before, and find its domain. So Laplace transform f of t, again, we know that is integral 0 to infinity e to power minus st f of t dt. And I can write this one as integral 0 to infinity e to power minus st times e to power at dt. My f of t is e to power at. And then I can write this one, same base, different powers. So I can just add the powers. And then I'll get integral 0 to infinity e to power minus s plus a t dt. And I can write this one as limit h goes to infinity, integral 0 to h, e to power minus s plus a times t dt. And I can write this one as limit e to power minus s plus a t divided by minus s plus a, integral from 0 to h goes to infinity. The antiderivative of e to power minus s plus a times t dt is e to power minus a plus a times t divided by minus s plus a. Remember again, the integral is respect to t. So anything other than t is considered as a constant. So minus s plus a here is a constant. And then if I plug the limits, apply the limits, then I will have this function evaluated at h minus this function evaluated at 0. So then I'll have limit h goes to infinity e to power minus s plus a times h divided by minus s plus a minus 1 over minus s plus a, this function at 0. E to power 0 is 1, so minus 1 over minus s plus a. And then I will have 1 over s minus a plus this limit e to power minus s plus a times h divided by minus s plus a as h goes to infinity. Now again, similar to before, I can consider different cases. If s is equal to a, what happens? The original expression, if s equals a, then e to the power minus at times e to the power at will be 1. And integral 1 dt 0 to infinity, we just saw in the previous example, is divergent. Therefore, the Laplace transform will be divergent if s is equal to a. So this will be divergent if s equals a, again, because, integral 0 to infinity 1 dt is divergent. What about if S is less than A? If S is less than A, see S less than A, then A minus S will be positive. So I have minus S plus A. So here I have minus S plus A. And if S is less than A, what can I say? I can say that then A minus S will be positive. So this expression here will be positive. And as h goes to infinity, a positive number times infinity, e to power infinity will be infinity. Therefore, this term will be divergent, goes to infinity, and the whole expression also goes to infinity. So I can say that, again, divergence happens. Divergent if S is less than A, because if S less than A, then minus S plus A will be positive. And here I will have e to power positive times infinity, which will be e to power infinity, and e to power infinity is infinity. And finally, if S is bigger than A, I will have convergence. So convergence if S is bigger than A, because in that case, minus S plus A will be negative. And then here I'll have e to power negative times infinity, which will be e to power minus infinity. And e to power minus infinity will be 0. So minus S plus A will be negative, and e to power minus infinity will be 0. So convergent to which number? E to power minus infinity is 0. So this will be 0 over something which is 0, and I will have convergence to this number. So if I want to be more specific, I can say equals 1 over S minus A. So it is convergent, but specifically it's convergent to this number, 1 over S minus A, because then the other term will be e to power minus infinity, which will be 0. 0 over something is 0. And then 0 plus 1 over S minus A will be 1 over S minus A. So the answer will be 1 over S minus A if S is bigger than A. So that means Laplace transform f of t, which can be also denoted with capital F of S, is equal to 1 over S minus A if S is bigger than A and is undefined. If S is less than or equal to A. So that means domain of Laplace transform f of t, which is equal to f of S, is the interval a to infinity, because for S bigger than A, the function is defined as equal to 1 over S minus A, and otherwise is undefined. So the domain is a to infinity. So this is consistent with what we derived before for 1. 1 was e to, if A is 0, then you will have e to power 0, which is 1. See, we are considering e to power at here. So if A is 0, I'll have e to power 0, which is 1. And we already saw that the Laplace transform is 1 over S in the previous example. Here also, if I replace A with 0, I will have 1 over S minus 0, which is 1 over S. And we saw that the domain is 0 to infinity. And here also, if I replace A with 0, the domain turns out to be 0 to infinity. So this is the example for Laplace transform of e to power at, which is 1 over s minus a if s bigger than a. Now the next example, show that Laplace transform e to power minus at times f of t is equal to capital F of s plus a for a piecewise function f of t, and in above, capital F of s is the Laplace transform of f of t. So let's assume we have access to Laplace transform of f of t. Let's say it's capital F of s. Then if we multiply this f of t with e to power minus at, then the Laplace transform will have a shift. Will go over a shift, and f of s will change to f of s plus a. So if you here you have e to power minus at, then here you have f of s plus a. So naturally, this means that if here you have e to power at, here you would have f of s minus a. So, for example, we saw Laplace transform of 1 is 1 over s. Laplace transform 1 is 1 over s. This is what we saw in the first example. So here, f of t is 1. Then Laplace transform e to power minus at times 1, according to the formula above, will be equal to f of s plus a, which will be 1 over s plus a. If this is your f of s, if this is your capital F, this is your small f of t, this is your capital F of s. So this formula says if I multiply small f of t with e to power minus at, the answer will be capital F of s plus a. And if this is capital F of s, capital F of s plus a will be simply 1 over s plus a. So that means Laplace transform e to power minus at will be equal to 1 over s plus a. And this is consistent with the previous example, because in the previous example, we showed that Laplace transform e to power at is 1 over s minus a. If Laplace transform e to power at is 1 over s minus a, then Laplace transform e to power minus at will be, of course, 1 over s plus a. You just need to change a to minus a in this formula. Now, let's try to prove this formula here. So proof of formula above. Laplace transform e to power minus at f of t is equal to f of s plus a. So I want to prove this formula. First, I gave an example where we can apply this formula. So this is just an example of this formula. It's not a proof for this formula. So I always say in all math courses that I teach that if you want to prove a property, you cannot prove it by examples. You have to prove in general. Examples could be helpful to give you some idea, but they are not considered as proof. So this is just an example of this formula, but it's not the proof. Proof has to be valid in general, not with examples. So now we want to prove that formula, which of course has to be valid in general. So let's start with Laplace transform of e to power minus at f of t. So this, according to the definition, is integral 0 to infinity e to power minus 8 st times this function here. Times this function here, which is e to power minus at f of t dt. And I can write this one as integral 0 to infinity e to power minus s plus a. So see this one, e to power minus st times e to power minus at will be e to power minus st minus at. I can factor minus out, and also t is a common factor. T is can be also taken out. And then I'll be left with minus bracket s plus a times t times f of t dt. And this is exactly capital F of s plus a if capital F of s equals 0 to infinity e to power minus st f of t dt, which is Laplace transform f of t. If you set Laplace transform f of t, which is defined this way as capital F of s, which is what we did before, then capital F of s plus a will be this expression with only one difference, where s has to be replaced with s plus a. And this is exactly what is happening here. S is replaced with s plus a. But other than that, this is the Laplace transform of f of t. So we showed that Laplace transform e to power minus at f of t is equal to capital F of s plus a, where capital F of s is the Laplace transform of f of t, and it's defined as integral 0 to infinity e to power minus st f of t dt. So this is a general formula that you can apply for any function. We applied it for, we saw if we apply for f of t equals 1, we get the result that we saw in the previous example. But of course, we can apply it for any function f of t here. We'll see more examples later.